Last section, we talked about how we can deal with differential equations that are in systems. So, and matrices are great for handling systems of equations. So it shouldn't be surprising that we are now going to introduce matrices with our differential equations. So typically, or before, we've dealt with matrices that only had constants in the entries, but we can deal with a matrix value function, so sometimes referred to as a matrix function, where each entry is not just a number, but an actual function. So it might be a column matrix or a column vector. So notice that this is x vector of t, and he has components x1 of t, x2 of t, all the way to xn of t. Or he might even be an m by n matrix, where each entry is not just a number, but an actual function. Okay? So since they're actual functions, we can even talk about taking derivatives of these guys. So if x of t equals e to the 2t cosine of t and t cubed minus 3t, x prime of t, who would that be? Well, let me give you a second to find him, and then we'll do it together. So if we take each piece and do his derivative, the derivative of e to the 2t is 2e to the 2t. The derivative of cosine of t is negative sine of t, and the derivative of t cubed minus 3t would be 3t squared minus 3. Okay. And what if we had not just a column vector matrix, but a matrix function that's not just a single column? We can find a prime of t by taking the component-wise derivative with respect to our independent variable t. So we will get 0 cosine of t, negative e to the t, and 2t. And the good news is that the derivative rules that we've learned in Calculus 1 will still hold true. So the derivative of a sum is the sum of the derivatives. The derivative of a product is first times the derivative of the second plus derivative of the second times the first, just like we learned in Calculus 1. Okay. And so let's take advantage of this matrix notation to help us convert this system that we saw at the end of class or into the video last time into a matrix equation. So if we look at this as a matrix valued function, x vector prime, because each one of them is derivative, and we could even look at this right here as f vector. Then if we let the p of p's be the coefficients, and then the x vector be the x1, x2, x3, xn, okay, we could then write this as this form: x prime equals p of t as a matrix times the x vector plus the f vector. So let's see how that works here. So let's rewrite this system as a matrix equation, and we'll identify each component. So we'll take this guy right here, and this will be x vector prime. So x vector prime equals p of t times the x vector. And notice how we had no entries after the x2s here. So the f1 of t would be 0 and f2 of t would be 0. So, but let me just write that plus f of f vector up here. So x is going to be the vector x1, x2, and technically those guys are functions of t. If you wanted to write that, you could. Okay. And x prime would be x1 prime of t and x2 prime of t. P of t would be the coefficients. In this case, they're actually just numbers, 2, 3, 2, and 1 as rows. And f of t, we decided, is 0 and 0 because he's homogeneous. Now, let's take and go to the next step, and we're going to verify that these guys x1 vector, be careful that that's different from the x1 function, but the x1 vector is different, is this guy right here, and the x2 vector, not x2 function, is this guy right here. We want to show that they're each solutions to our matrix differential equation. So let's go ahead and verify that. So if we've got x1 vector is negative e to the negative t, e to the negative t, then x1 vector prime would be e to the negative t and negative e to the negative t. So keep that in mind. And so that's kind of the left-hand side of the equation. Let's see what the right hand is and see if that is in fact the same as the left-hand side. So let's do our matrix. And our matrix was 2, 3, 2, 1 times the x1 vector, which was negative e to the negative t and e to the negative t. Notice that this is p times x vector plus f of t was 0, so we can ignore that. We'll get matrix multiplication row by column, negative 2 e to the negative t plus 3 e to the negative t, and then negative 2 e to the negative t plus e to the negative t, which simplifies to be e to the negative t and negative e to the negative t, which, if you'll remember from just a second ago, is x1 vector prime. So we have just verified that the x1 vector does in fact satisfy the differential equation, the matrix equation here. I'll give you a minute to show that x2 prime also satisfies. And then we'll come back together. So here I took x2 vector and I did his derivative. I did the matrix times the x2 vector and found out that we got the exact same thing as the x2 vector derivative. So this is a solution. Sorry, x1 is a solution and x2 vector is a solution as well. And since they're each solutions, we can do a scalar multiple of one plus any scalar multiple of the other, and they will still all be together a solution. Let's see that in action. So if I let x of t vector be c1 times x1, so that would be negative c1 e to the negative t, and then c1 e to the negative t, and I'll do plus c2 times x2 vector, so that would be plus 3 c2 e to the 4t plus 2 c2 e to the 4t. Let's check and do the same kind of work here and verify that that also is a solution for any choice of constants c1 and c2. So x1, or the x vector, overall vector prime, is going to be, take the derivative of this, we'll get c1 e to the negative t plus 12 c2 e to the 4t and negative c1 e to the negative t plus 8 c2 e to the 4t. And then let's go ahead and take and do our matrix. So p times the x overall vector is going to be 2, 3, 2, 1 times our vector of negative c1 e to the negative t plus 3 c2 e to the 4t and c1 e to the negative t plus 2 c2 e to the 4t. So we should get negative 2 c1 e to the negative t. So row by column. So we do this guy right here times the whole thing. So plus 6 c2 e to the 4t. And then do this guy times all of that guy. So we're going to have 3, plus 3c1 e to the negative t, and then plus 6c2 e to the 4t. Good thing I caught myself, so row by column. And now let's come down here. That's going to be a negative 2c1 e to the negative t plus 6c2 e to the 4t. So this guy times this guy, and now this guy times this guy, plus c1 e to the negative t plus 2c2 e to the 4t. And when all the dust settles and all the like terms are combined, negative 2c1 plus 3c1 is c1 e to the negative t. And the 6c2 e to the 4t plus 6c2 e to the 4t is plus 12c2 e to the 4t. And then combining terms here, we get negative c1 e to the negative t and plus 8c2 e to the 4t. And you'll notice that this is the x overall vector prime. And so he does satisfy the original differential equation. And we better stop there so I can get this posted.